cut your hair.
One year, somebody, for reasons unknown, made a pile of wire on the tabletop and then hot glued the wire to the tabletop. And the thing about that is that it's like fiberglass, right? It's a fiber reinforced polymer. It's strong.
Yeah.
We tried, chiseling it off and scraping it, and finally we heat gunned it until it melted, and then scooped the whole goo into the trash. But so what do you think about Wednesday? Should we skip class again and go directly to the lab on Wednesday? Is that a good idea again? Since Thursday's the due day for the... Okay, so Wednesday will be no lecture. And any questions about current lab, about parallelization or weird errors you've seen? Questions about memory?
How many multipliers did you say were again?
There are, if you look at the data sheet for the where did I put that? I think I put it in lab 3. There's a table. We have an SE A5 grade, and the logic, there's 32,000 ALMs, 85,000 logic elements, 128,000 register bits, 480 MLab blocks, and 87 multiple precision DSP blocks, which translates to 174 18 by 18 multipliers, because there's 2 independent 18 by 18s for each DSP block. 2 18 by 18s, 2 19 by 18s, 1 27 by 27 multiply per DSP block. So that's the number. Did you run out?
Yeah, with the current way I'm running it, but more efficient.
And currently you're just brute force parallelizing individual nodes? Yeah, I think to meet the criterion, you have to put at least 2 nodes in each state machine using 1 multiplier between them. What else? So who's got a column parallelization simulating? It's working the way more or less. Any tricks, any weirdnesses that you found?
I think integrating with memory is a little tricky. So like to start with, I was using the memory IP block, and that didn't, so there was a mismatch between simulation and the actual functioning. So simulation was just a cycle delay, whereas in actual hardware it is like it is yeah. So in actual hardware the delay between the latency between data read and like the read address is 2 cycle delayed. So then there was a mismatch. So then I fixed the simulation. So then I got a perfect match between simulation and the actual hardware. So then it started to work.
So the when you use the mega module, the simulation module which is generated has an incorrect delay.
Yes.
It needs one extra cycle
Yeah,
delay.
So then what I did is I took the template for M10K. So there's like an HDL template. So I used that to simulate, and then it showed proper 2-cycle delay in the simulation, and then it started to work.
When you say template, you mean the from the HDL style guide?
Yes.
Interesting.
So which template was it from the style guide?
Dual port RAM,
Dual port RAM.
dual port RAM template from the HDL style guide.
So the IP as is doesn't simulate well with model sims. So I didn't figure out why it was behaving incorrectly. So I'll spend some time and see like what is causing the issue, but it didn't.
Okay,
Sure.
when you find out, put a post on Piazza. Yeah, thanks. Anything else? Any other observations about memory? Anybody tried MLab blocks? Any other questions about Lab 3? So we decided a few minutes ago that there would be no class on Wednesday. Go directly to lab. Well, let's talk some more about Lab 4. I looked, did a Google search on Mandelbrot FPGA and Mandelbrot Verilog. Interestingly, one of the hits for Mandelbrot Verilog is a Verilog solver for Mandelbrot sit on DE1. Turns out that's not our board. The DE1 is different than the DE1-SoC. The DE1 is this very odd board with a big Altera FPGA and an Atom core on it, and a PCIe bus connecting them. So you can certainly read that, and if you end up using some code like that, or using fragments of somebody else's code, you have to acknowledge it clearly in your listing and in your lab report. And there's lots of solvers out there. So they're not that hard to find, but if all you do is copy in somebody's solver, then clearly you need to add something. One interesting aspect of this is that the serial bottleneck representing the bus connecting your solvers with the VGA may be the slowest piece of this. Maybe the rate limiting serial bottleneck. There's a way of speeding this up. It's slightly painful. And that is, don't use the VGA defined by Qsys. Write your own. Writing a VGA state machine is not hard, and in fact has been done by several students and actually documented on the website. And once you do that, then you could remap the VGA completely to dual ported M10K blocks and refresh the VGA completely simultaneously with writing to it. Then you would have to write your own serializer that takes the output of several solvers and serializes them onto the VGA. But it might well be faster. I would say don't do this as a first hack, folks. Let me see if I can remember where the VGA stuff is. Haven't thought about it in a year or so. VGA examples. So on the VGA page, all of these are based on a VGA control module that was written by Skylar Snyder. He fixed a bug in the Thoracic distribution. The Thoracic distribution had assumed 0 latency on the memory. Ooh! So he replaced it with a either variable 1 or 2 cycle latency so that it actually works correctly. The symptom was that the whole screen was moved that way 2 pixels. And you brute force, using this module, you brute force put together a VGA control signal, VGA async, vsync, blanking signal, so on. And you manually associate a display memory with the VGA. And then once you've manually hooked up that display memory, you can dual port it, use a read port to do nothing but read to the VGA screen, and use a write port to do nothing but write results in. But get it running first with the Qsys VGA abstraction, because you got plenty to do on this lab in 2 weeks. First thing to do is, of course, you're going to simulate a solver. You're going to simulate one pipe, complex pipe, in Model Sim, and you're going to simulate it until the number of iterations required for the Model Sim simulation is the number of iterations required by the MATLAB simulation. For, let's say, 3 or 4 or 5 different complex points. 1 or 2 inside the Mandelbrot set, 1 or 2 on the edge of the Mandelbrot set, or just outside. And when it matches for 3 or 4 or 5 points, you can be pretty sure you got it right. Again, once you've got that running, once you've got the solver running, then you want to include the VGA state machine so that you can, the VGA busmaster state machine, so that you can make sure that your whole path works up to the busmaster module, just as you did in lab 2. Questions? So thinking a little bit more about this iteration, what we're going to be iterating is z real plus j zi times z real plus j zi plus c. Let's make it cr real plus jci. And we're going to want to write. We're going to want to convert this to a hardware description. So, what I did was first of all to write out a kind of a block diagram of what operations had to occur, and then I tried to merge them, and then tried to minimize the number of cycles necessary to make that go. So, if we go through that process, we have some z real as input, and remember this is now step n. We have some z real and some zi, and we're going to put this into both inputs of a multiplier and square it, and we're going to put these both into leave myself a little more space, put this into inputs of a multiplier and square it. And then we need a cross product, so we're going to put both of these into yet another multiplier. And then these two are going to be summed along with CR to form ZR n plus 1. And this is going to be then multiplied by 2. And added to CI to form Z imaginary at time n plus 1. And then, of course, n is going to be incremented to form n plus 1 because we have to keep a count. Then, to find out if we're done computing, we're going to square this. We're going to square this, sum these, and ask, is it greater than 4? Is the sum greater than 4? And if the answer is yes, we're going to draw some color corresponding to outside the Mandelbrot set because it diverged. If the answer is no, we find out is n greater than 1,000 or whatever you choose. And if the answer is yes, we draw a point inside the Mandelbrot with the appropriate color for inside the Mandelbrot set. And if the answer is no, we go back and do it again. One, two, three, four, 5 multipliers. So first thing in optimization is to fold this and say these two multipliers are really doing exactly the same operation, just one step ahead of these two multipliers. So we're going to say that Z real equals ZI equals 0, and we therefore know how to initialize ZR squared and ZI squared. And so we will not only use these two values for determining if we're done, but we will save them for the next iteration and feed them back in and eliminate this multiply and this multiply. So we've dropped it to 3 multiplies. So let's say that the limiting resource is multipliers. I don't think it is in this case, but let's say that it was. the limiting resource were multipliers, then we could arrange a solver with a minimum of 3 cycles, one cycle for each multiplication, that use those 3 multipliers to solve one iteration. On the other hand, if you've got enough multipliers, it may not be worthwhile trying to optimize on minimizing multipliers because you're going to run out of something else first, like memory bandwidth or logic elements or access to the Qsys bus or something else. So let's say that you decide to use 27-bit multiplications here. Each one of these multipliers will be exactly 1 DSP block. So for 27-bit, which sounds reasonable, 27-bit you could do, say, 3.24 or 4.23, depending on how much you worry about overflowing this. And you still have 87 multipliers. So if you used 3 per pipe, you could still do, what, 27, 28 pipes. That's a lot. So maybe that's not a rate limiting resource. Maybe what you do instead is you parallelize it by saying we're going to do all 3 multiplies at the same time. And try and get the whole result, one iteration done in 1 cycle or maybe 2 cycles. How much state do you have to maintain for each iterator? From cycle to cycle, all you need is Z real and Z imaginary, or the square of those. Actually, you need both. So you need, because you need the product of these, so you need either 3 or 4 words depending on how you arrange it, which suggests that even if you have 28 or 30 solvers, you'll still only be using something like 150 words of 150 27-bit words of memory of registers. You may as well just use registers and not worry about memory blocks at all for the solvers. Pull the results out of registers, put them back in registers, and use all of the, if you wanted to, use all of the onboard memory as a VGA buffer. So in terms of memory bandwidth to the display, is it possible to come up with a way? So some regions are going to be solved. Some regions of this complex plane are going to take 1 iteration to diverge. If it's up near the corner of the compute region at say +1 +1, then the divergence time is going to be 1 cycle, 1 compute cycle. If you're right in the center, the divergence time is going to be 1,000, because you'll go to maximum and it will never diverge. Maximum count, it will never diverge. That would suggest that, I mean, certainly if you have a new result on every cycle, you're not going to be able to write to memory that fast. If you have 30 solvers and each one's trying to write on every cycle, they're all going to be waiting on the average 29 cycles or 30 cycles or so. So is it possible to come up with an order of computation that mixes continuously long computations with short computations? So you try and mix up the points that have a length of 1,000 iterations with points that have length 1. I don't think so, but maybe. Well, let me put it this way: if you're doing the whole Mandelbrot set, then there's regions of coherency in complex space. So this whole region, this circle, is guaranteed to, every point in there is guaranteed to run for 1,000 times, 1,000 iterations. And so if you were scanning across a scan line here, you would, every computation would take 1,000. On the other hand, if you're running across a scan line here, every computation would be of length 1. So maybe this will work. Maybe if you have one solver going across this line and another solver going across this line, you're kind of mixing up the long and the slows, except most of them are going to be are long and fast. The fast ones are going to be a lot more numerous than the slow ones because there's more vertical space here. But maybe it'll balance. I don't know. Don't know. Is it better to scan this way for load balancing, scan this way, or to design blocks and use and dispatch blocks to processors? Certainly, if you're near the edge, let's say you've zoomed in right here, then there's going to be a lot of cases, maybe the majority of the computation is going to be on the edge. On the edge, and going from point to point across here, you're not going to know whether you're inside or outside, and so the computations will be mixed. There'll be some fast ones and some slow ones as you scan in either direction, horizontally or vertically. So it may be that you get some geometric help once you've zoomed in. You can choose any kind of color map you like. You can see you can start to see numerical limitations here. There's kind of like fuzziness or oddness here, and kind of broken up into dots. Somebody at Cornell 24 years ago or so showed that the Mandelbrot set was simply connected. So there are no disconnected regions. But some of them get pretty thin. So if you have limited numerical accuracy, these pieces start to look disconnected. So think about load balancing here. You could do this in MATLAB. You could ask, if I start 4 different processors running along 4 different lines through the image, how long does it take each one of them to finish? Not in seconds, that's boring, in terms of total number of iterations calculated. And if they all come out about the same, then you're load balanced. So what if you were to then say you're going to statically distribute on 4 processors, you're going to statically distribute this stripe to processor 0, the next stripe to processor 1, the next stripe to processor 2, the next stripe to processor 3. You could add up all of the iterations for each of the processors and ask how close is it to load balance just because of the geometry as opposed to, say, anything dynamic that you're doing, like choosing where to put the next point. So if you're playing around with parallelization, high level, how would this load balance, does it make any sense? Do it in MATLAB. It's easy. All you got to do is count, make an iteration counter. I think I even did that. Because I was trying to figure out how many No, I didn't do that here, but you'd, before you iterate a region, you'd just start an outer counter that sums up the number of n for each different point that it calculates to get the number of iterations for the whole region. And you could play around with load balancing scenarios that way very quickly using high-level stuff. I thought I did that in one of these. I probably did, if only I could find the right one. No, not there. Okay. And again, you're probably going to want to use the HPS for timing, for parameter entry, for the center of zoom, for the to display the elapsed time on the VGA, stuff that's just kind of painful to do in Verilog, but easy to do in C. And there is a time of day counter on that's running in Linux with a resolution of a few microseconds, so I may as well use it. So maybe a resolution of a few nanoseconds, actually. I think that the core timer is running at CPU speed. So what do you think? What's on your minds? FPGA project for Xilinx. Woo! Embedded SOPC design with Nios 2 processor. Well, close. So there's lots of information out there on various aspects of Mandelbrot solvers. Yeah, some guy was coding it on a Commodore VIC-20, which I believe was a 6502. I coded it on an Apple II, which was also a 6502. This would have taken an hour and maybe 2 hours to do a floating point version on a 6502. half-hour hacks. Yeah, well, maybe. Oh, here it is. Mandelbrot on an Altera DE1. But, as I said, this is not the DE1 SoC. Wow. That's appallingly slow. So, so what else? What else do you need to know at this point? What do you need? How's again about Lab 3? What do you want to know about Lab 3? What's hard here? Who's got 256 nodes running on the hardware? Anybody? How many nodes you got running? You got 256 nodes running on the hardware?
I got like 5,500 by 10.
500 by 10 running, okay. So 500 one way and then striping it, so you should be able to just increase the striping and get it wider. And how does it sound? Does it sound like a drum or does it sound like a piece of hit steel?
It sounds more like steel because it is like thinner.
Right, sounds more like banging on a saw.
Yeah.
Yeah. Interesting. Anybody else got 256 nodes? Again, I would say that the fastest way to get to 256 nodes is going to be to put 2 nodes on each state machine and run the thing in flat parallel. Except each state machine is going to calculate 1 node and then the next node. And that then is 1 time step jump forward. Right? Let me remind you that I did put a few notes in here on the RAM style and the mult style synthesis parameter that allows you to control the kind of memory that you're going to implement by instantiating it directly in Verilog. So you can do one of these 2 formats. You can say, I want a byte wide RAM with 64 words, and then say synthesis RAM style you can't say M512 because that doesn't exist on our chip, but you can say M10K or MLab. And again, this thing that looks like a comment and is a comment as far as your simulator is concerned, has to be before the semicolon. To get the timing right for M10K blocks, I believe that you have to, in your Verilog, insert pipeline registers in the input. That's true, yes. You have to insert pipeline registers in the input and use the templates given in the HDL style guide. Has anybody tried this style of comment? I don't know what a parentheses star does. Is that also a comment? I don't recognize that syntax. HDL style. So starts out multipliers, multiply adders, multiply accumulators, memory. synchronous memory blocks. So the very first examples in this are bad examples. These are the ones you don't do. It says, whenever it says not supported, don't do it. They should have put these at the end. Not supported. Okay, so, and you are probably, unless you do something really odd, like read and write from the same address at the same time, you should tell the compiler, there's a comment you can put in, you should tell the compiler that you don't care about that condition. You're never going to do that. That's silly. I'm not going to do it. And then the compiler will not generate the hardware necessary to ensure write after read. Single clock synchronous RAM with old data read during write behavior. So this is just exactly what I said not to be true. And here we have that we have a write enable. We're going to write, but in any case, we're going to read the data that was already in that module. But this does not have the pipeline registers in it. You have to add those, the input pipeline registers. Otherwise, you get incorrect timing. So this is almost
I think there's another example after this.
that has the pipeline registers in it. That's VHDL.
I think it's
Towards the bottom. Avoid coding this style.
Yeah, this one is like more similar to what we want. So instead of using clock 1 and clock 2, we can just have a single clock. So this has a register for the read address that gives the extra read.
This has a register for the read address. That is certainly true, but not for the write address. So you'd have to add that for the write address. Or do you? No, you don't, as long as you're not writing it back on the same. And this one is not registered, I don't believe. So, watch the timing on memory blocks. Do you want to post the memory module that you were using that matched the
I'll post the Mandelbrot code on Qsys.
Yeah, put it up on Piazza as soon as possible, okay? And that'll avoid the ambiguity of getting the simulation timing right for memory. Thank you. What else? Anything else? Okay, folks, no class on Wednesday, and Friday starts Lab 4. It is split across spring break. There'll be a week before spring break, a week after spring break. Spring break doesn't have to be 9 days long.